In this video, we're going to prove the arithmetic as well as the geometric sequence. They are examinable. Even though there is proof of the infinite series, it's not examinable, so that one we're not going to show in the video. All right, so let's start with the proof of your arithmetic sequence. Sn is equals to n over 2 into 2a plus n minus 1 into d. All right. So how do we start about that one? So the first thing that you're going to do is that you're going to let a represent your first term, and then you let your d represent constant difference. All right, so then we start. We're going to start by saying our sum Sn is equals to A O. Sn is equals to the normal formula, our formula of the arithmetic sequence, which is A plus n minus 1 into d. And remember, these are sums, so we have to add something. All right, so what are we going to add? The variables that we are always concerned with is your a and d. All right, so we're going to add d on this one. We take the first term, which is a. To get to the second term, we know that we have to add the constant difference. Okay, so in this case, the OR part will then mean that we're going to have a plus n minus 1, n minus 2, sorry, because it's a second addition, into d plus. So to get to the third term, what we do, we add d again, creating a 2d. So that means we're going to have a plus 2d let me just put this in brackets so that you can see it's one thing. A plus 2d and in this case it's going to be n minus a 3 in the bracket. So now we have the addition of the third term, which is a plus n minus 3 into d. All right, and then that's going to go on and on and on and on. So we'll say plus dot dot plus dot dot. She's gonna go on and on and on forever. So what we're going to add now as the last three terms is these terms reversed. These terms reversed, and then these terms reversed. Okay, So we just say a plus n minus 3 into d plus a plus n minus 2 multiplied by d, and lastly plus a plus n minus 1 multiplied by d. And this is our equation 1. And then this one is going to be a plus 2d. We're taking these terms reversed. A plus 2d plus a plus d and the last term being plus a. And this is equation 2. Okay, so what is the next step? The next step is that we add equation 1 and equation 2. Add equation 1 and 2. Equation 1 and 2. Okay, so what are we going to have? Sn plus Sn is going to be 2Sn. Sn plus Sn is 2Sn equals to a plus this term, that will be a plus a, that is 2a, then we have plus n minus 1 d. N minus 1 into d. Plus we add this one and it's going to give us the same thing. A plus a will give us 2a. D plus, so this one if you multiply it out is going to be nd minus 2d. So we will have nd minus 2d plus a d, which is minus d. If we take d out as a common factor, then we're going to end up having n minus 1 into d. Okay, let me just put them in brackets. Then we have plus this term plus this term, it's also going to give us the same thing. This will be 2a. You can just multiply this out, then you will see you will end up with 2a plus n minus 1 into d. Plus dot 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 plus, if you take this term and add it with this one, it's going to give us the same thing. We're going to end up with 2a plus n minus 1d. Okay, so this is going to be for 3 times again, plus this one, that one, plus that one. You will also get the same thing, 2an minus 1d plus 2an minus 1d. Please write it down when you are asked to prove this. Write that formula twice, 2 more times. I'm just writing a dash there just to save time of the video. You will notice then that it's the same thing that is being added over and over and over again. So what we can then say, we can say, okay, this is n multiplied by 2a plus n minus 1 into d. Okay, we have 2sn on the left hand side. It keeps on looking like a 5. Okay, it's not easy using an electronic pen. SN. All right. So that n then means that means you can add this 2a n minus 1d up to the number where you are required to stop. So that means if s and n was 5, you're going to have 2a plus n minus 1 5 times. Okay, that's what n is for. All right. And then now we're going to divide both sides by 2 so as to make Sn subject of the formula. This then means that Sn is equals to n over 2 into 2a plus n minus 1 into d. Remember, this is examinable. That means it's possible to get it on a test or an exam. So you do need to know how to prove your arithmetic sequence, which is the sum of the arithmetic. So this is a series, sorry. This is a series because it's a sum. Sn is a series, which is a sum of an arithmetic sequence. All right, so now we're going to do the proof of a geometric series. All right, so with this one, where do we start? All right, so we're going to start the same way that we started with this one. We first let a represent the first term. We let a represent the first term, and then we let r represent the constant ratio. All right, so how do we go about this one? So now we're going to say Sn is equals to, how do we go about determining the geometric series? All right, we say Sn equals to the first term, which is A, plus, how do we get the second term? We multiply it by the constant ratio. So that means we're going to have AR. We multiply by the constant ratio. And the third term will be multiplied by the constant ratio also. That means it's going to be AR squared. And the fourth one, still the same, will multiply by R. So we're going to have AR cubed. And then we're going to do this plus dot 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 up to our geometric sequence, of which the formula is AR to the power of n minus 1. All right, this should be our equation 1. The next step, you multiply your equation 1 by R. Multiply equation 1 by R. All right, so Sn times R is going to be equals to R Sn. Equals to A times R will be equals to AR plus AR times R will be equals to AR squared plus AR squared times R is going to be AR cubed. Plus dot 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 plus, now we're going to have AR n to the power of minus 1 plus a to the power of AR to the power of n. And now we have our equation 2. Then what do? We say equation 1 minus equation 2. We're going to next say equation 1 minus equation 2. All right, so Sn minus Rsn, so that would be Sn minus Rsn equals to A minus a 0 is A. We are subtracting like terms. AR minus AR is 0 plus AR squared minus AR squared is 0 plus AR cubed minus AR cubed is 0 plus dot 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 plus ARn to the minus 1 minus AR to the power of n minus 1 is 0 plus 0 minus ARn is minus ARn to, so AR to the power of n. Okay, so do notice here that we have a common factor Sn. So we're going to take Sn out as a common factor. Then we are left with Sn divided by Sn is 1. Rsn divided by Sn is R, equals to 0, 0, 0 is 0, but then we have common factor A in this case. So if we take our A out as a common factor, we are left with A divided by A is 1 minus AR to the power of n divided by A will be R to the power of n. Dividing both sides by 1 minus R, then we end up with Sn is equals to 1 minus R to the power of n. Forgot the A. It's A into 1 minus R to the power of n divided by 1 minus R. So we proved this formula. And then you go on and say similarly. Similarly, if we got here, if we were to say equation 2 minus equation 1 instead of equation 1 minus equation 2. So you say equation 2 minus equation 1, then it was going to give us Sn is equals to A into R to the power of n minus 1 all over R minus 1. And that is the end of a proof of a geometric series. It's examinable, so you might get it on a test or an exam. So you have to know it by heart.